Hello class! In this lesson, in activity 9.1, we're going to be comparing models in 2D and 3D dimensions. If we were back in class, we would be using marshmallows or my favorite, gumdrops. You probably don't even know what dots are. I love them. It's a really old candy that sticks in your teeth. I love them. We would be using those to model some of the particles that make up air. All right, we are starting to learn the difference between atoms and molecules. When I use the word particles, particles works for all of those tiny, 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 smaller than microscopic units that matter is made out of. Okay, but today we're going to kind of start to look at the difference, how these atoms would actually combine to make very familiar molecules that you may have heard of. All right, so if we look at your book on page 75, it says we need to make a key for the colors of gumdrops we would be using to represent the atoms. I don't have any gumdrops. Oh, I don't have any gumdrops at home, so we're just going to use modeling clay instead. All right, and I've got pink, white, green, and black. Now, I'm just thinking ahead and I'm preparing you for some of these colors that we tend to use as scientists. Oftentimes, when people are modeling molecules, they tend to use the same color for carbon. Usually scientists use black for carbon. Now, atoms themselves don't really have color. I mean, they're so tiny, so tiny that you wouldn't even be able to tell what kind of color it was unless you had a ton of them. Once you start to get lots and lots and lots and lots of carbon atoms together, then you can see its color. And carbon does tend to be black-ish in color. Like, think of maybe a brisket that somebody would use in a grill that has a lot of carbon in it. So in your key, please shade the carbon atom dark. If you're going to use your pencil, you can just shade that in. I'm just going to use a gray marker so that you can still see the little C for carbon underneath. You know what? I've got to move my face so you can actually see my key in the video. Choop, 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 choop. What if I go like that? Let's move it. There we go. Yay! It'll take a minute to focus. Okay, so we've got carbon figured out there. Now, another very common atom that gets modeled a lot is oxygen. And in pictures that you find on the internet, you're going to see that scientists tend to use like red in order to model out an oxygen atom. Oxygen is not red at all. So don't even ask me why they use that color. Oxygen, actually, if you have a lot of oxygen and it's in liquid form, if it's in gas form, you can't tell what color it is at all. But if you have a lot of it and it's in liquid form, it's almost clear, but a tiny little bit blue. It's like bluish clear. Nobody has a bunch of liquid oxygen hanging around though, because it's so combustible. It just very easily could burst into flames if you had like a wood splint or anything flammable near it, which is pretty crazy. So we're going to use the closest I've got to red. We're going to use pink. So my pink little clay ball is going to represent oxygen. So please, if you happen to have pink, color in your atom pink or just write pink above, like so. Carbon, all right, gray or black. All right, usually nitrogen stays white when I'm modeling it out with my other kits. So I'm just going to leave my nitrogen white. away. And hydrogen, whoa, 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 whoa. Oh, shoot. I misspoke. Hydrogen is white. Nitrogen, we're going to say, is green. Sorry, guys. Got ahead of myself. All right, so let's shade nitrogen green. If we were really using marshmallows or gumdrops, we would just use whatever colors we had in the box or in the bag. All right. We're just going to be creative. All right. So we're going to use this clay to build some very familiar molecules. The first familiar molecule, which you may have heard of, looks like this down below in your box. It has 2 oxygen atoms with a carbon in the middle. So I'm going to make one of those. I've got 1 oxygen already. I've got 1 carbon. Woo! I'm going to need another oxygen. And we're going to smush it together to represent the attractions that these atoms have for one another. Joop! It just so happens that this one kind of forms a molecule that's linear. That means that the oxygen is right next to the carbon on both sides, and usually carbon likes to be in the middle. So we put the black one in the middle. That's true of lots and lots of other molecules that carbon is in. All right, we call carbon the backbone of organic chemistry, of living things. There's a lot of oxygen in living things. Okay, so now that I have my model made, I'm going to color in my 2-dimensional model on my sheet of paper. And have you guessed what this molecule is called? This is carbon dioxide. Carbon dioxide. If you're like, how does she know what that's called? What? There's actually a key of the molecules we're making right up here in number 2 of the procedure, if you're wondering where I came up with that word. Okay? But a chemist will recognize this molecule by the name because they know that carbon is here, is present, and dioxide means 2 oxygen atoms, 1, 2, on either side. Carbon dioxide. All right, let's keep going. On the right, they want us to make a molecule that has 1 oxygen and 2 hydrogen. All right, so I've got an oxygen, I've got a hydrogen, I need another hydrogen. And when I smush them together, they are not in a straight line like carbon dioxide. They're kind of off-centered. It's off-centered because of rules that you've started to learn in your Legends of Learning games. You started to learn that some of these atoms have a special configuration as far as where the electrons hang out in the orbitals. I know you were building some of these atoms virtually in the games you were playing this week. And this is just like additional knowledge. It's like extra knowledge you don't really need in 6th grade yet, but you will have to learn it eventually. So the more you hear it, the better. Water is a polar molecule. All right. That means it is shaped like this and not like carbon dioxide. All right. And we would call this H2O or water. Here, I'll write H2O next to it. And carbon dioxide would be CO2. All right, now that my 3-dimensional model is made, I'm going to color in my two-dimensional model on the paper where I'm going to shade in my oxygen atom pink and I'm going to leave my hydrogens white. Woo, we are flying through this. I'm feeling good. Just two more to make. Nitrogen. You know, some of these elements, they prefer to travel in pairs. And nitrogen is like that. Nitrogen travels 2 by 2. When it travels 2 by 2, just like so, it just makes it more stable and it's less likely to react with other matter that it comes in contact to in the environment or in contact with. So my nitrogen molecule could be called N2, and I write it out as nitrogen. I'm getting that name from up here. All right. And now that my three-dimensional model of nitrogen is made, I'm going to color in my two-dimensional molecule here. Oh my gosh, I just noticed up here I wrote nitrogen instead of green. Oh man. There we go. I fixed it. Mrs. Soik, too much coffee or not enough? I've been very well behaved. I have not been drinking very much Diet Pepsi while I've been home in quarantine. And I'm missing it. Okay, we got one more, oxygen. Oxygen also travels 2 by 2 like girls going to the bathroom. I only say that so that you remember it for the rest of your life, okay? Oxygen is actually pretty dangerous when it travels by itself. It can actually be very harmful to us when it travels by itself because it would react with lots of other stuff. Like in a chemical reaction, it would oxidize. So when oxygen travels 2 by 2, like girls going to the bathroom, they have a very special, strong bond. It's a very strong bond called a double bond between these two. Again, this is more information than you really need to know in 6th grade, but you'll need to know it eventually. So as much as you hear it repeated, the better. Now that my three-dimensional model of oxygen is made, I'm going to color in my two-dimensional model, and we're going to call that O2. This is one molecule of oxygen. Both of these atoms are also called oxygen. So oxygen atoms in the air that we breathe tends to form a molecule called O2 with two atoms bonded together. It's not actually the only oxygen molecule we have in the air around us. If oxygen were to combine with 3 oxygen atoms, we call that ozone. Have you heard of ozone before? All right, well, let's leave that discussion for another day and take that away. Now, it says, in step 3, after a class discussion, answer, air is made up of what percentage of each type of molecule? All right, let's find out. This website that tells us what air is made out of. It says the air you breathe is made of lots of other things besides oxygen. Oxygen only makes up about 21% of air. About 78% of the air you breathe is made up of other gas called nitrogen. There are also tiny amounts of other gases like argon, carbon dioxide, and methane. Plant and animal life on Earth can't survive without air. Take a deep breath and click on Find Out More to find out more. All right. When we click on Find Out More, we also find out that the rest of air, about 1%, is made up of other gases like carbon dioxide, methane, helium, and a couple other gases. That's not all. There are lots of very tiny particles suspended in the air you breathe, like dust, microbes, spores from